Okay, here we go with another couple of related rate problems. The conical cup is 6 centimeters across and 6 centimeters deep. So if it's a cup, it'd be sitting like this and like that. Conical means the shape of a cone. 4 meters across, that'd be the diameter. 6 meters deep would be... Water leaks out the bottom at a rate of 2 cubic centimeters per minute. Looks like a rate to me, so this tells me the related rates. How fast is the water level dropping? That's also a rate when the height of the water is 3 centimeters. Okay, so first of all, we have water in here somewhere, and we have a depth to that water. Okay, and what we know is the depth to diameter ratio is always going to be the same as the original. So right now we have a diameter to depth ratio of 4 to 6, which is 2/3. So that means that 2/3 is equal to diameter divided by depth. You know what? Let's change this to radius because we're probably going to have to deal with radius anyway. So let's say the ratio of radius to height is it'd be 2 to 6, in other words 1/3. So that means that radius is equal to h over 3. Or h is equal to 3r. Okay, so there's my r, there's my h, I guess. Okay, so what are our variables? We've got an r, and we've got an h, and we've got an icebox over here. So let's make sure we've got all of our letters labeled. Water leaks out of the bottom at a rate of... So this, what is that? That represents, since we're losing water, that means we're losing the volume of water. So that right there is dV dt, 2 cubic centimeters per minute. Okay, how fast is the water level dropping? That would be dH dt when the height of the water is, when h is 3. Okay, why did I put it in the icebox? Because we want to know when the rate of change of the height at a certain moment of time, not all the time. So it has to be, keep it in the icebox till we take the derivative, then we can bring it out. Okay, so now we need to write an equation. It looks like we just need to relate height and volume. Well, the volume of a cone is 1/3 pi r squared times height. That's the volume of a cone. Problem is it has an r involved in there. We don't want an r involved there, but we have this little relationship up here that r is equal to h over 3. So I can rewrite this as volume is equal to pi over 3 times h over 3 squared times h. And we can simplify that too. That'd be 3 squared is 9, so that'd be 27. So we'd say pi over 27 times h cubed, because we have h squared times h. So that's my formula that relates volume to height, or in this case depth. And we take the derivative of that, and so we get dH dt is equal to pi over 9 h squared, I'm sorry, dV dt, pi over 9 times h squared dH dt. And we're trying to find dH dt at this moment in time. So we're just going to plug in all the things we know. So I'm going to put a little error here saying going this way. It's because I don't have room to go down. So dV dt is going to be replaced with, oh, and that would have been a negative because it's leaking out, right? So that'd be a negative 2 centimeters cubed per minute is equal to h is 3, so that'd be 3 squared would be 9. So the 9's would cancel out, so that'd just be pi dH dt. So that means dH dt, oh, I do have some room down here. dH dt is going to be equal to that divided by pi. This would have been centimeters squared in here, right? So this is centimeters squared. So we divide centimeters cubed by centimeters squared, and we get just centimeters, which makes sense. So that would be -2 over pi centimeters per minute. And that would make sense with the changing height. So the height is changing that much centimeters per minute. And it's shrinking, of course. Okay. Here, a person 2 meters tall walks towards the lamppost at level ground at a rate of 5 meters per second. Oh, there's a rate. There we go. The lamp on the post is 5 meters high. How fast is the length of the person's shadow decreasing when the person is 3 meters from the post? Aha. So here's the lamppost shining. Here's the person walking towards the lamppost. So he's moving that way. And what happens is the rays of the light go off the top of the guy's head and make a shadow. So then we got to put some things in here. Person 2 meters tall walks. Okay, so where was I? So we need to start label some things. The lamppost is 5 meters high, so that's just going to be labeled as 5. The person is 2 meters high, so that'll be labeled with 2. What are the things that are changing? Well, so he's moving 0.5 meters per second. So that would be the change in this value and that value. We've done one, I think we've done like this one recently, or one like this. How fast is the length of the person's shadow decreasing? So, okay, so we want to call this, we'll call this L for length of shadow. And we can call this X or whatever for the distance from the post, okay? And that'll work just fine. So now the question is, what is this 0.5 meters per second? Well, that is both change in X and change in L, isn't it? So if he's moving, oh, actually, no, that's not true. Sorry. That would be the change in X, but L, remember, is the distance, because when he moves this way, the shadow is also moving with him, but shrinking. So this would not be the same as that. Okay, so this is dx dt, 0.5 meters per second. Okay. Need a little ice box over here. Ice box. And so what are we trying to find? It says how fast is the length of the person's shadow decreasing? So that's dy dt. We don't know. When the person is 3 meters from the post. So that would be when x is equal to 3. Okay. So now we need to set up an equation that relates x and y. No problem, because we got similar triangles here, because this little triangle here is similar to the big major triangle, right? So we could write an equation like 5/2 is equal to L over x plus L. Because L would be the length, I'm sorry, other way around. I put 5/2, so I should put x plus L on top and just L on the bottom. Because L is in the triangle with 2 and x plus L is in the triangle with 5. Okay? So, to solve this, before we take a derivative, I'd probably multiply both sides by 2L just to get rid of that stuff. So that'd leave me with 5L and 2x plus 2L. And now we're going to take the derivative of both sides. So that would be 5 dl dt. That would be 2 dx dt. And that would be 2, or whoops, plus, that'd be 2 dl dt. subtract 2 dl/dt from both sides. You notice there's the same, so that would be 3. Oh, wait, why am I doing that? I know what dl/dt is, right? Oh, dx/dt is 0.5, so I would replace that with 0.5. And yes, I would subtract that from both sides, so I would have 3 dl/dt is equal to, because I subtracted 2 from the 5, is equal to 2 times 0.5. So that means, oops, that was weird, just split it. So that would mean that dl/dt is equal to, say 2 times 0.5 is 1, divided by 3 is 1/3. And that would be in meters per second. Here's yet another one. This is a little bit different than some of the other ones we've done, so it'll be interesting. So the boat is being pulled into a dock by attached. A boat is being pulled into a dock by attached to it and passing through a pulley on the dock, positioned 6 meters higher than the boat. Oh, that's confusing sentence. Sorry about that, folks. If the rope is being pulled in at a rate of 3 meters per second, rate, there we go. How fast is the boat? There's another one, approaching the dock when it is 8 meters from the dock. So let's draw a little triangle here. Once again, we got a dock here, right? And the rope is attached up here to a pulley, and it's going like that. And here's the boat. There's the motor. Here's the water level, right? So it's being pulled in. The boat is being pulled into a dock by attached to it. I don't know what that says there. I'm passing through the pulley on the dock. So this is 6 meters higher than the boat. So this would be 6 meters. The rope is being pulled in at a rate of 3 meters per second. So the rope is being pulled in. That means this rope right here. So we could call that R for rope. Rope is being pulled in. That would be dr/dt at 3 meters per second. How fast is the boat approaching the dock? When it is 8 meters from the dock. So put a little ice box over here, and we say how fast is it approaching. So that's this distance here. That's how far the boat is from the dock, not the R. The R is a diagonal thing. That's how long the rope is. They're asking how fast is the boat approaching. So how fast is this distance changing when this distance is 8? So let's call this x. So that means we put x equals 8 in here, and we put dx/dt equals, I don't know. So let's write an equation that relates x and r. Well, it looks like pretty obviously we might use a Pythagorean theorem there because that's a little triangle. We'll say the rope is attached down here or something. So that would be 36 plus x squared is equal to r squared. So if we take the derivative of both sides there, we get 36 disappears, of course. We get 2x dx/dt. We get 2r dr/dt. And so then we plug in everything we know. Well, we know that x is 8, so that'd be 16 there. We know that dx/dt is what I'm looking for, so I'll leave that as dx/dt. We know that 2 is 2, of course. We know that r is, we don't know what r is. We have to find it. So we're going to go over here and make my box a little bit bigger because this is actually happening inside the box, right? We would have, when x is 8, that means we'd have 36 plus 64 is equal to r squared. And that would be 100 is equal to r squared, which means r is 10. So we'd put a little 10 in there, so that'd make that 20. And dr/dt is 3 meters. Is it negative 3 meters or is it 3 meters? How fast the boat is approaching is being pulled in at 3 meters. So that means r is changing it's getting smaller. So that'd be a negative 3 meters per second. So we would put a negative 3 meters per second in here. Let's see, that was meters right there. So put a little meters there. And that was meters also. Put a little meters there. So we're going to end up with meters squared per second, and then we're going to divide by that. So we'll get back to just meters per second, which is good. So we end up with dx dt is equal to 3 times 20 is 60, so that'd be negative 60 over 16, and that would be meters per second. Again, I know it's meters per second because that's meters times meters, and we're dividing by meters, so just leave me with meters per second. Of course, we can simplify that to, what, negative 30 over 8? Oh, no, how about negative 15 over 4? Meters per second. Okay? Oh, the classic ladder problem. I'm going to do this, and then I'll be the last one for this video. Okay, a ladder 10 meters long is leaning against the vertical wall. So there's my vertical wall. There's my ladder. Ladder is 10 meters long, so I can put a 10 right in there. The top end of the ladder is sliding down. So this is sliding down. So that means this distance is changing. It's getting smaller. So that'd be y. We'll call that x. So it says the top of the ladder is sliding down the wall. When the top end is 6 meters from the ground, it is sliding down at 2 meters per second. How fast is the bottom moving away from the wall at this moment, at this instant? So all that stuff is inside the ice box, apparently. Top of the ladder is sliding down the wall. When the top end is, so when y equals 6, it is sliding down at 2 meters per second. So that means dy dt is 2 meters per second. Negative, because it's sliding down. How fast is the bottom? That would be dx dt, moving away from the wall at this instant. Okay, so as this ladder slides down here, that means this would have to slide out the side. Okay. So we need to write an equation that relates all these things. Pythagorean theorem seems to fit the bill. So that'd be y squared plus x squared is equal to 100, because that'd be 10 squared. We take the derivative of both sides, so that'd be 2y dy dt plus 2x dx dt is equal to 0. Okay, so again, we didn't set this equal to 0. We just took the derivative of both sides and it happened to be 0 on one side. Now we're going to plug in all that we know. We know that y is 6, so this would be 12. dy dt is what I'm looking for. X I don't know, so we need to find it. I think it would be 8. We could do that real quick. That would be 100 minus 36 is 64. Yep, that'd be 8. So that'd be 16, and dx dt. No, dy dt I know. Whoops, I said we didn't know that. We do know that. Back up. So that would be negative 2 meters per second plus 2 times 8 would be 16. dx dt is the one I don't know. Equals 0. Okay? So that would be negative 24. Oh, 16 is, that's meters. Yeah. So we're going to move this over to the other side and divide by 16. So we end up with dx dt is equal to negative 24 divided by 16. And notice this is going to give me, when I move this over, that'll be meters per second. Oh no, this is meters out here. So that'd be meters squared per second. And I'm going to divide by meters, so that bring it back to meters per second, which is good. And that's negative 24 over 16, which would actually be negative 3 over 2 meters per second.